Hello everybody. Here are the solutions for the problems from the second exam review. So problem 1 here is basically just a quotient rule problem. And I'm not going to go over the details of that particular one because it's very easy to do. Right, basically we're looking at the function x squared plus 1 over negative x cubed, and that's something that we can easily compute the derivative of. Instead, I'll move on straight to problem number 2, which is looking at a function m of x defined as x squared, and we want a tangent line to the function f of x, which is m plus x divided by the product m times x plus 1. And we want a tangent line at x equals 0. So let's go ahead and first take the derivative of this in order to figure out the slope of our line. So f prime of x, of course we're going to need to use quotient rule. So it's the derivative of the first, which is m plus x prime times the bottom mx plus 1 minus the top m plus x times the derivative of the bottom prime, just like so, all over the bottom squared. And now we just compute these derivatives. So we have what? The derivative of m is 2x, the derivative of x is 1, so I have 2x plus 1 times m times x is going to be x cubed plus 1 minus now m plus x is going to be x squared plus x, and then this is multiplied to m times x is x cubed plus 1, but I'm taking the derivative of that, so I actually need to, since mx is x cubed, the derivative of that is 3x squared, because this is x cubed plus 1 prime. So I get 3x squared, and that's the derivative because the derivative of 1 is 0. So that's the top, and then the bottom, I'm just squaring this. So I have x cubed plus 1 quantity squared. And I'm evaluating this when x is 0. So anywhere I see x, that's going to disappear, which means this term is going to be 1 on top here, minus, this is just 0, divided by 1 squared. So the slope that we have at x equals 0 is 1. We also need the y coordinate, so I need to compute f of 0. That's going to be equal to, okay, well, I get 0 on top because x is 0 and m of 0 is 0 divided by 1. So that's 0, which means the equation of the tangent line is going to be y minus 0 equals the slope, which is 1, x minus the x-coordinate also of 0. So this is the line y equals x. And that's it. That's the answer for this particular problem. Now let's go ahead and look at problem 3. So what do we have for problem 3? I have the following. I have a function f of x, and I'm defining this to be x minus 1. And I'm looking at a new function now, g of x, which is f of x plus 1 divided by f of x. And I want to know where this has a horizontal tangent or a vertical tangent. Okay? So for x values, does this function have those properties? Well, I need to take the derivative of g. So g prime of x is the derivative of the top, which is just f prime, times the bottom minus the top, which is f plus 1, times the derivative of the bottom, which is f prime, all over f squared, the bottom squared. So, okay, f prime is just 1, times f is x minus 1, so this is 1 times x minus 1 for this term, minus f plus 1 is just x times f prime, so times 1, all over x minus 1 quantity squared. So what is this equal to? I have 1 on top, I'm sorry, I have x minus 1 minus x over x minus 1 quantity squared, so this is negative 1 over x minus 1 quantity squared. And notice g prime is never 0 because of that. The top is never going to be 0, the numerator is never going to be 0, and the limit as x approaches 1 is going to be of g prime is going to be negative infinity because of this negative 1 on top. So what does that mean? That means that at x equals 1 we have a vertical tangent. And another way we could have figured this out is, okay, g of x is as, this is just the function x over x minus 1. That gives you, that denominator there gives you the vertical tangent at x equals 1, right? That's the asymptote of the function g of x. So that's problem 3. Problem 4, what do we have here? We have something similar, except now we have just a different function. So I'm not going to go over the solution for that one. I can talk about it in class if you prefer, but it's solved in a similar way to problem 3. Okay, and so then I'll move on to problem 5, which is a little more interesting. So let's go ahead and see what we have for problem 5. For problem 5, I'm looking at the function x squared, and I want to see for what point, at what point does the line passing through the coordinates 2, 2 and 3, 3 intersect the graph of my function f. So first I need the equation of this line, and that means I need the slope. So the slope is the change in y over the change in x, and of course the slope here is going to be just 3 minus 2 over 3 minus 2 is just 1, of course, because as I increase the x coordinate by 1, the y coordinate increases also by 1, so they increase at the same rate of 1. And then I just have to write an equation for this. So y minus 2 equals x minus 2 times 1, which means this is the line y equals x. And in order to find the intersection points, I set my function, which is x squared, equal to x. So these intersect at x equals 0 and x equals 1. Okay, so in fact, if I want the y coordinate also, this is 0, 0 and 1, 1. That's where x squared intersects y equals x. And as a graph, what this looks like is, like, let's say this is up at 1. This is what the intersection will look like between that parabola and y equals x. So that's what's happening. So that was problem 5. Nothing too crazy about that. Problem 6 is basically another tangent line problem. So let's see what we have. We have the function x cubed, and I want the tangent at point 1, 1, and I also want the normal line. So for the tangent, first I need to find the derivative. F prime of x is going to be 3x squared, and when I evaluate this as x equals 1, I get a slope of 3. So the equation of the tangent line is y minus 1 equals 3 times x minus 1. So if I distribute the 3, I get y minus 1 equals 3x minus 3. I can move the 1 to the other side, but basically this is an acceptable answer here as well. So that's that part of the problem. And now for the normal line, we have to figure out what the slope of the normal line is going to be. And to do that, I have to show you a few examples. So let's say that I have the line y equals 2x here. Something that's perpendicular to that is the line y equals negative x over 2. So the slope here was 2, the slope here is negative 1/2. And in general, it's true that if I have something with slope 3, I can take the opposite reciprocal, and that would be the slope of my normal line. I'm still going to use the same point 1, 1, except now I use this slope. So the equation of the normal line is y minus 1 equals negative 1/3 x minus 1. That's the normal line, or the perpendicular line to the graph. Okay, so normal is just another way of saying perpendicular. Problem 7, I'm not going to go through it because it's not too complicated. Basically, you just want the derivative of that function at x equals 0, so you plug in 0 for x. It's a problem that is going to involve product rule, and so there's nothing too crazy about that. So I'll move on to problem 8, which has us compute quite a few derivatives. Let's see what we can do with problem 8. I'll start with part A. Part A is just product rule, so there's nothing too special going on here. If I'm looking at the function x squared plus x times x plus 1, the derivative of that is going to be the derivative of the first, so that's 2x plus 1, times the second, plus the first, x squared plus x, times the derivative of the second, which is just 1. And then of course you can simplify from here and all that. I'm not going to go through the algebra. That's that's something that is just going to take too much time. Let's move on to part B. I'm looking at the function x squared minus 3x minus 10 all over x plus 2. And notice that if I want to take the derivative of something like this, I can actually rewrite this function as, if I factor, it's going to be x minus 5 x plus 2, so these multiply to minus 10 and they add to minus 3, and this is divided by x plus 2. I can cancel that, so the derivative is the same as the derivative of the leftover part, which is x minus 5, so that's 1. Of course this is except at x equals negative 2, because I removed that point from the domain of the function. So that's this problem. The derivative would be undefined there. There's no need to do quotient rule because we can factor it so easily. Part C, we have a chain rule problem here. So I'm looking at 3 plus 4x minus x squared raised to the power of half, and the outer function is the 1/2 power. So I'm going to bring down the 1/2, and the new exponent is negative 1/2. And of course inside I have the original inside function, which is 3 plus 4x minus x squared. But now, because of chain rule, I need to multiply by the derivative of this inside, and that's 4 minus 2x. So that's the derivative here. Let's do part D. Part D is another chain rule problem. So I'm looking at the function x divided by 1 plus x to the 5th. And what's that? Well, the outer function is the 5th power, so I have 5 times something to the 4th for the derivative, and inside I keep the original inside. But now I multiply by the derivative of this inside, and of course I'm going to need to use quotient rule for that. So it's derivative of the first times the bottom minus the top times the derivative of the bottom, all divided by 1 plus x squared. So then this is just, you can simplify from here, etc., but the calculus part is done. Part E now has a combination of product rule and chain rule because of this square root part. So the derivative of this is derivative of the first, which is 4x times the second, unchanged, plus the first times the derivative of the second, so that's 1 over twice the square root 2 minus x, times the derivative of the inside, which is negative 1 due to chain rule. So this whole piece is the derivative of this square root part over there. So that's part E. Part F, again, I'm not going to do because that's just a combination of chain rule and product rule, and we've seen something very similar in class. Instead, I want to move on to problem 9. So problem 9 is a little more involved because it involves multiple chain rules. So the function that I'm looking at is parenthesis, I'm just going to copy it down, x squared minus 1 cubed plus some other quantity here, and inside that I have another parenthesis. This is raised to the 4th, and everything is to the power 1/2. Okay, whenever I'm looking at something like this, of course I need to identify the outermost function. That's the raising something to the power 1/2, and the derivative of anything like that, anything that has a square root, looks like 1 over twice the square root. Inside, I copied the original inside, so I have x plus 5 over x squared minus 1 cubed plus this part, so I have x plus 3 quantity squared plus 9. This is raised now to the 4th power, and now let me make some more room. Now I start applying chain rule. Okay, so now I have to multiply by the derivative of this, whatever's under the radical here. For the first one, it itself needs a chain rule. It's something squared, and inside I have x plus 5 over x squared minus 1 times the derivative of this very inside, so times the derivative of the fraction, and that uses, of course, quotient rule. So the derivative of the first times the bottom minus the top times the derivative of the bottom, which is just 2x, all over x squared minus 1 quantity squared. So that's the derivative of this cube here. Now I also need to add a derivative of this part. So that's 4 times something cubed, because that's the outermost here. Inside I keep the original, so x plus 3 quantity squared plus 9. And now I multiply by the derivative of this inside, which is just this part, because the derivative of 9 becomes 0. So this becomes 2 times the quantity x plus 3 to the first times 1, which is the derivative of x plus 3, close parenthesis, close big parenthesis. So inside this chain rule piece, I'm really having the derivative of that plus the derivative of that here. So that's what's happening. It's quite a complicated problem. It involves a lot of steps, but if you keep track of everything and you go slow, you're going to get the right answer. Okay, so that was problem 9. Basically, so far we've been just doing some basic derivative things. Now we're getting to things that are a little more involved. So we're getting to implicit differentiation. So problem 10, and I'll start with part A. I want to find dy dx for the function 2y squared equals y plus x. So I'm taking a derivative with respect to x while treating y as a function of x, which means on the left side here I'm going to end up with 4y dy dx comes from chain rule equals dy dx plus 1. The derivative of x with respect to x is just 1. And now I move all the dy dx terms on the left side. So I have 4y dy dx minus dy dx equals 1. Whatever was originally here, I'm left with the 1. Factor dy dx. So you're left with 4y minus 1 equals 1. And finally we divide, and we find that dy dx is equal to 1 divided by 4y minus 1. Now so this was part A. Part B of this question is basically asking us to do the same, but now I need to find the x dy. So let's take a look. Now I'm looking at this same equation here, except I'm taking the derivative with respect to y. So on the left hand side, I'm just going to be left with 4y equals 1 plus dx dy, and that means what? That means that dx dy is equal to 4y minus 1. And it's no coincidence that these are exact reciprocals of each other. It's exactly how it should be, right? So if dy dx is 1 over this, then the dx dy is the reciprocal of dy dx. So that's the connection between the two. I'm not going to go ahead and do part C and D because they are extremely similar. The only difference, we have a mixed xy term, so that's going to use product rule for that second term, that x times y. So that's problem 10, right? So fairly straightforward. Now let's move on to problem 11, and I'm going to start with a new sheet of paper here because I feel like this is going to take a little more room to solve. So problem 11 here now is telling us the following. We have y of t, so we have two functions, y of t equals t cubed, and x of t is 1 minus t squared, both vary with t, and we want to differentiate the equation x cubed y plus xy cubed equals t squared with respect to t, the variable t. Let's see what happens. So I take the derivative here with respect to t while treating both x and y as functions of t. Here, of course, I'm going to have to use product rule for both terms. So I get the derivative of the first, which is 3x squared dx dt from chain rule times y plus the first, so x cubed times dy dt. So that's the first part. Now here I'm going to get, of course, dx dt times y cubed plus x times 3y squared dy dt, and on the right hand side I'm just going to get 2t. So that's the derivative part. Of course, we know the formulas for x and y of t, which means y prime of t is just 3t squared and x prime of t is minus 2t. So I can plug these into here, and this is for dy dt anywhere I see it, and then doing some algebra I actually get a formula that depends only on t. So that's problem 11. I'm not going to go ahead and write everything, it's a lot of writing, but it's fairly clear what to do. Problem 12 is telling us to look at x squared times x squared plus y squared equals y squared. So I have some curve that depends on x and y, and I want to find the equation of tangent line at the point root 2 over 2 comma root 2 over 2. So let's see. Of course I need to find dy dx, and I'm going to do that using implicit differentiation. Here it's a product, but it's actually going to be probably easier if I distribute this x squared. So let's rewrite this function as x to the 4 plus x squared y squared equals y squared, and now I take the derivative with respect to x. So 4x cubed plus 2x y squared plus x squared times 2y dy dx equals 2y dy dx here. I move all the dy dx terms on the left, so I'm going to get dy dx, and what I have is I have 2x squared y minus 2y, and I move everything else that doesn't have dy dx on the right side, so it's going to be negative 4x cubed minus 2x y squared. This means what? This means that dy dx is equal to the following. We have, I'm going to factor out the minus sign, so I'm just going to have 4x cubed plus 2x y squared on top, and on the bottom, because I'm factoring out the minus sign, I'm going to bring it in the bottom and flip the order of these, so it's going to be 2y minus 2x squared y. And I'm evaluating this when x is equal to root 2 over 2 and when y is also equal to root 2 over 2. So let's go ahead and plug in that for x. So I have 4, 8 in the bottom, 2 root 2 on top. So that's the x cubed part, because if I cube this, I'm going to get 8 on the bottom and then 2 root 2 on top, plus I have 2, x and y are the same value, so I'm actually going to get, again, 2 root 2 over 8, everything divided by, okay, 2y, so I can't get away with it now, I have to write just the root 2, minus 2 times 2 root 2 over 8, right, because x squared y is just 3 of these guys, which is just like above 2 root 2 over 8. Okay, now let's see, can we simplify this and how? Here's how I'm going to do it. I'm going to write 8 of these over 8 instead of just 1, and then I'm going to cancel all of the 8s in the denominator, right? Imagine I factor an 8 out of here and an 8 out at the bottom and just cancel that. So what I'm left with is that dy dx at this particular point is equal to 8 root 2 plus 4 root 2 divided by 8 root 2 minus 4 root 2. So 8 plus 4, that's 12 root 2 divided by 8 minus 4 is 4 root 2, and I get just a slope of 3. All the roots cancel very nicely. So this is my slope. So that means the equation of the line is y minus root 2 over 2 equals 3 times x minus root 2 over 2, and we are done. That's it. Problem 13 basically is just another one of these problems where I have to use implicit differentiation, and also I have to find a second derivative instead of the first. We can do that in class if you want to. I don't want to spend too much time on this video with that type of stuff because it's a lot of computation. Instead, I would rather take a look at the word problems. So let's see, problem 14. I have a circle and I have the radius dr dt is changing at a positive rate of 2, so the radius of a circle is increasing, and I want to find how fast is the area changing. In other words, what is dA dt when the radius is precisely 2. So okay, let's take a look. What is the area of a circle? In terms of radius, a is equal to pi r squared, and because these are both changing with respect to time, I'm going to take the derivative of this equation with respect to t. So dA dt has to equal to pi times 2r dr dt, which comes from chain rule. And I know what dr dt is, I know what r is, so dA dt is going to be pi times 2 times r, so r is 2, dr dt is 2, so pi times 8, or 8 pi. The units here are going to be, well, if this is in centimeters per second, as the problem states, then this is going to be in centimeters squared per second, right? Because it is a unit of area, so I have to square the centimeter part. This is of course increasing, and it makes sense. If you're increasing the radius of a circle, the area should also increase, so the rate of change has to be positive, just like we got. Now let's take a look at 15. I have a spherical balloon that's filling up at a rate with air at some rate, right? Which, if something is filling up with air, that's something that has to do with volume. So I know that dV dt is equal to plus 5 cubic centimeters per second, and also the unit here kind of gives you a hint that it should be volume. And the question is, how fast is the radius changing? Well, I know that the relationship between volume and radius for a sphere is v equals 4/3 pi r cubed. And if I want to find how fast the radius is changing, I need to find dr dt. Okay, well, that means I want to take the derivative of this equation with respect to time. So dv dt equals 4, the 3 is going to cancel, so it's just 4 pi r squared dr dt. I know r because I'm doing this when the radius is 2, as the problem states. 2 squared is 4, so I get 16 pi equals 5, and then dr dt here, which means dr dt is going to equal 5 over 16 pi centimeters per second would be the appropriate unit here, because it's a unit of length, so we only get centimeters to the first power here. So that's the answer for 15. Let's go ahead and do 16 now, another word problem. So what do we have? Problem 16. We have two variables, x and y, and they are related by the equation x squared plus 3 equals y. And we're told that both of these change with time. We need to find dy dt, but I'm told that x is equal to 1 and dx dt is equal to 2 at that instant. So the way I'm going to do it is, of course, I'm going to take the derivative of this equation with respect to time. So I get 2x dx dt equals dy dt. So that means dy dt is equal to 2 times x was 1 times dx dt is 2, so it's just 4, and that's it. So this is a very straightforward problem, nothing too complicated. Let's take a look at 17. I have a pebble dropped in a calm pond and it's causing a ripple in form of a circle. Right? If you ever dropped a piece of rock in water, or even a drop of water in water, you see that there's concentric circles emanating from the origin and moving outward. And now we're told that the radius of this ripple in the water increases at some rate. So I'm told that basically dr dt is equal to, and the rate here is 1 foot per second. I'm also told that I need to find how at what rate the total area is enclosed is changing when r is equal to 4 feet. Well, just like before, the area of a circle is pi r squared, and I need to find dA dt, right? How fast is the area changing? Well, I take the derivative of this equation with respect to t, so I have dA dt equals 2 pi r dr dt. I know dr dt is 1, I know r is equal to 4, so that means dA dt should be 4 times 2 is just 8 pi square feet per second. That's the answer. Next we have problem 18. So I'm told that we have some kind of cube and the sides are all expanding at the same rate, causing the volume of this cube to increase at a rate of 5 cubic centimeters per second. Okay, I want to know how fast is the side length increasing, So I'm going to call this side length L, or you can call it X if you want to. But I know that the volume is L cubed, and basically I want to find the L dt for the first part of the problem at least. Well, let's take the derivative with respect to time. So dv dt should be equal to 3L squared times dl dt, and I'm told that I want this when L is equal to 10 centimeters. So I plug in 10 for L, so dv dt, which is 5, should be equal to 300 dl dt, which means dl dt is equal to 5 divided by 300, and you can simplify that, but basically this is what we have. And the next part of the question is how fast is the surface area changing? And the surface area of a cube is 6 times L squared, because the area of a single face, well, since it's a square, is L squared, and there are 6 total faces for a cube. And I need to find dA dt, so let's take the derivative with respect to time here. I get 12L dL dt. So this is going to be 12, L is 10, dL dt we found in the previous part of the problem, that's 5 over 300. So okay, I can cancel some stuff here, I'm left with 30. I can cancel more stuff, I'm left with 6 in the bottom. 12 over 6 is equal to 2, and that is the rate of change of the surface area. And of course the units here is centimeters per second for the length, for the side length, and here it would be centimeters squared per second increase in surface area, or the rate of change of the surface area. Let's see, we have problem 9, it's a physics problem, problem 19, I'm sorry. So we have the position function, and we want to find when the particle is at rest during the first second. So basically for that one, you take the derivative, you find where your velocity is 0. If it's during the first second, great. If not, then you say no. So I'm not going to go over that, I can do it in class in detail. The same with problem 20. So we want to find for what values of t is the particle at rest, which means I need to look at the velocity and figure out where it's equal to 0. So I just take one derivative, set it equal to 0, and so on. Problem 21 basically is a critical point problem, absolute min and max. That's something that we've seen quite extensively in class, and I'm happy to go over the problem again, but I won't do it in this video. And the same with problem 22. So I'm not going to go over the solution for these, but you can ask me in class and I can show you there what is going on, just because the video is already becoming kind of long. We're at almost 40 minutes. So that's pretty much it for these review problems. It's not too complicated. I think maybe the more challenging part is the word problems here, but I can talk about those in class, strategy on how to approach them. So that's it for this exam.